National Mexican Prize on Science and Arts of the year 2008, and he's also at the international level a member of the Statistical Physics Commission of the International Union Theory of Applied Physics. So we are very happy to have him here for this short visit. And well, here you have what he's going to tell us about. Thanks for coming, Alberto.
Thank you very much for the introduction. And happy to be here confined to this area. I'm nervous that I would say something that I would not like to be reminded of sometime in the future. And anyway, let's just begin with this talk, which in fact contains two analogies. Analogies generate all the time some sort of satisfaction or some insight. On some occasions, you will judge yourselves. These analogies are between a very well-known, familiar teacher in nonlinear dynamics, known from the early 80s, late 70s, early 80s, in low-dimensional nonlinear systems, classic, one of the roots to chaos known as the root via intermittency. And the analogies are, in one case, to a typical problem in the physics of condensed matter. I will go through it briefly, and then another analogy is focusing somehow generally in complex systems. So this is the outline of the talk. So one analogy is to the problem of localization of transport in disordered systems or quantum systems. And the second analogy has to do with these omnipresent laws of C and therefore. So let's just go quickly with the introduction. This is for the very few of you that may not be familiar with this nonlinear dynamics, iterated maps. So you just have a nonlinear function. You have two types of quantities. You have a control parameter C that you're going to move around carefully, and you have another variable x which defines phase space. We are only going to be talking about very simple one-dimensional systems, although you can think of the two variables C and x as being complex or being multivariate or whatever. And here I'm showing you this very familiar figure, this family of attractors of unimodal maps. In these kind of maps, you have present two different routes to chaos, one that goes via duplication of periods. So you have this Feigenbaum fig 3, and the other one that goes through the tangent bifurcation that I'm going to be talking about. So you can see it many, many times, both of them in these windows of different periods. But this is just an introduction. I copied some figures from a well-known book of the 80s, Schuster's book. And so I'm showing here, again, a cartoon of the previous slide. And I'm looking at a window of period 3, and here is the function, the map, composed 3 times. And then we focus on the neighborhood of a point of tangency with a straight line at 45 degrees. And then we have this typical situation in which you can be at tangency, or it can cut second to the line of 45 degrees, or it can be near tangency. If you are in this intersection case with epsilon less than 0, I haven't defined it. I should be here, perhaps the wrong slide. But in this case, you have a periodic attractor. If we're looking at this window period 3, you have 6 intersections. So you have 3 of them unstable, 3 stable, and you have a simple situation of long time behavior just becomes attracted to a periodic orbit. But if you are off tangency, you have a small neck through which the iteration goes through, and then eventually when it goes through it, escapes and bounces back and comes again at the left-hand side and does it when it goes through it, it appears as if it's almost periodic because it moves slowly through it, but then it bounces back, and so you have a sequence of laminar episodes interrupted by bursts, and the name of intermittency comes because of that. Well, this is the introduction, and now I'm going to talk a little bit about tangent bifurcation, and we go back to the, I think, the classic paper, which was at the beginning of the 80s, very a good period, the very first years of the 80s, like good wines. Every article of that time actually contains all the basic information of these problems. So this was, the authors were Bambi Hu and Joseph Rotnick. Bambi Hu usually makes the joke, you know, in Hong Kong, it's not uncommon to have an English name or something related. So he's actually called Bambi. I don't know what he's talking. And when he's in an audience, he says, Bambi Hu. And he was working with Joseph Rotnick in California. And then the interest was to look at this map, this neighborhood of the map of tangency, where you can make an expansion, and the expansion in general would look like this. First a linear term, then a nonlinear term. The most typical case is 2, of course, if there is no singularity in the derivatives. And the object, the aim, was to find out whether there is a special map or function, a fixed point map that satisfies this scaling relation. That means that functional composition is identical to rescaling as it is stated there. And they found out a solution, an analytical solution. That's what made it sort of interesting, their work. They thought this way: let's think of a different variable, not the variable x, but a variable which is just, say, y equal to x to a power to be determined later on. And they would say, if we look at this auxiliary variable, the map that actually obeys this scaling relationship, this fixed point renormalization, fixed point expression, should be a translation. Even in the book of Schuster, you find out that there is no simple reason why that should work. And I have asked Bambi, and he more or less concedes that he found it out, and then he just presented the properties that it has. When you have this, it is simple to corroborate just a few lines that in fact the function f star defined by this expression actually satisfies this expression, but also when it's expanded to the first few terms also obeys this expression. So this can be rewritten in the following way for the variable f of x. And here it is. And it has this abbreviation if you want. If you want to call this function a form exponential. And it has an inverse, which is this other function, so that there. When applied successfully, they give you the identity function. And I want to be very, very plain in my seminar today that this is only shorthand, that we should be careful to connect it with anything else. And I mean it because through the years, a presentation of this kind, it's taken as justification for with other implications. I want to be very careful about that. We're not talking about thermal systems at all. We're talking about simple math. We're only talking about shorthand. You can avoid it if you want. So if we use this shorthand, of course, this parameter q, if it's taken the limit towards unity, you recover the ordinary exponential, you recover the ordinary logarithm, and that's it. So something interesting is that the orbits or trajectories themselves, where t is the iteration time, the number of iterations, inherits the shape of the fixed point map. So here is the fixed point map that satisfies this equation, and here is an expression for a trajectory that has given initial value for the initial position. And it can be rewritten in this way, and I am putting a little square because we're going to use it later on. Okay, one can actually continue to determine what is an important quantity in the dynamics of nonlinear iterated mass, and that's the sensibility to initial conditions. And you can actually have an exact analytical expression for the sensitivity of initial conditions defined as this, and can be corroborated in particular, and this should be most of what I have to say with respect to the tangent bifurcation. For example, if your last thing is if you're interested in deterministic diffusion, you can use the tangent bifurcation to describe non-Brownian, non-Gaussian superdiffusion again in a comfortable analytical way. This is deterministic diffusion. Okay, now I'm going to go about localization. And what I want to say is the following. This is a very simple model designed in such a way that one can obtain analytical results, exact results. So you have a transport or electronic transport on a network, and the network is a double Cayley tree. So you have a number of leads and nodes, and this, as it's depicted here, it would be actually a regular network, not a disordered system for the moment. Or maybe for seminar. But I'm just going to show you that this is a very simple model in which one can work out the conductance across the network. And what is of interest is to see the behavior of quantities such as the conductance as a function of the size of the network, which is the number of generations that make it. The method that we use is basically type binding. We want to, or we could use transfer matrix formalism, or in this case, the scattering matrix. So you have an input for this corresponds to each node, and this epsilon should be the transmission probability or coupling between the nodes. So you have a scattering through nodes according to the leads that form this double Cayley tree. So you have a parameter epsilon, and you will have an energy term, which actually is measured by this lattice constant multiplied by this wave number. The North matrix is 3 by 3, but the system matrix is 2 by 2, and you have a recursive formula that you can work out if you follow the method. For example, that the matrix should be unitary, and then the time reversal or conservation of flux gives it in this special form. Also, the symmetry of the lattice allows you to only have two different elements only in the scattering matrix, and you can diagonalize it. And what is important then is to look at these eigenphases, and if you are able to determine the values of the eigenphases given the size of the network, then you have basically solved the problem. Let me say that the question of metal-insulator transition in a disorder system is open in the following way. The transition is mediated via a mobility edge, and what has proved to be difficult is to describe what happens at this transition, to sit actually at the transition other than to be near the transition, whether from the insulating phase or from the conductive one. So you have a recursion formula, and this would be then very simple. If you solve for the eigenphases, after writing one of them, then you can, through Landauer's formula, obtain the conductance G sub n as the size of the number of generations. But this is where the analogy lies. You can see that you have an iterated map here for the variable theta. And this is how the family of attractors look like. So for a given value of the transmission probability or coupling epsilon, and looking about the energy which through which the scattering takes place, you can clearly see that you have attractors of period 1 at these edges, at these bands, but you also have a chaotic phase, chaotic attractors, and you have precisely a transition between period 1 and a chaotic attractor. And the map here, I can show it to you for different values of the energy. The epsilon and the coupling is fixed, and you can observe the tangent bifurcation. The rest is just working along the problem in some detail. You can look at the sensitivity to initial conditions. You can obtain what would be the Lyapunov exponent. Here it is written for finite time or finite size of the system. When this number of generations goes to infinity, this becomes the Lyapunov exponent. It would be an exact expression. And here you have a recursion formula for the conductance, and for large n, you have this exact expression. What does it say? It says typically that the analogy is built on the equivalence between the Lyapunov exponent and the localization length, they being the inverse of each other. So that when at the transition, at the mobility edge, the localization length diverges, the Lyapunov exponent vanishes. So this line is not surprising. It just states the analogy and more or less what is the usual understanding close to a transition. But we can actually get at the transition, then the sensitivity to initial conditions is no longer an exponential. you see this the side of the period 1 attractor. The Lyapunov exponent is negative, and therefore any two trajectories converge to a single one, which is just the period 1 attractor. But when you are at the condition of vanishing Lyapunov exponent, what you have is not an exponential behavior, but because of we know what's the fixed point map, we learn exactly how the sensitivity to initial conditions behaves in that case. It's no longer an exponential, it's a deformed exponential. And the most general case would be that you have a non-zero curvature at tangency, and therefore you have this result. This would be then how the conductance behaves at the mobility edge, and here is just a numerical corroboration. In fact, you have a degree, as you would expect for that type of critical transition, a degree of universality. The conductance will decay basically with a slope which is fixed to be -4. And well, I wanted to show this analogy between behavior of a very simple map at the transition to chaos, and its manifestation in a problem that has to do with transport, in this case of electric charge. The way it's being presented is for a regular network, and you said, well, but the interesting, the important case is when there is disorder, and then one can actually continue along the way by recognizing that this apparently artificial double Cayley tree actually can be seen as a network of scatterers in disorder systems, because in localization in the disorder system precisely rests on constructive superposition irrespective of the positions of the impurities. So the double Cayley tree can be used to model the scatterers in a disorder system. But since my time is running out, I will go now to this second case. Well, you all know many things. I think I've heard about the law of shift, the ranking of functions. I like to show this often. I just found it in the web, but it has to do with Hungarian aristocracy in the 16th century, and how wealth was measured. And by the number of serf families they owned. So you could see that here is the number of owned families by that aristocracy, and that's the rank, and you can see that, you can see the numbers here, even the less wealthy owned something like 10 families of serfs. And the exponent here is close to 1. And you may also be familiar with the law of Benford, in which you just look at the first digit of data, say they are in decimal days. And here are 3 cases. It comes from a publication, I think, not by Negrini. And you have the law of Benford, tells you that the digits don't appear uniformly distributed, that the first digit appears more frequently than the second and the third and the fourth, and so on. It's a simple logarithmic law, which is the blue bars here, and that's it's in use actually in order to detect fraud, whether in income tax returns like there, or in other in the elections, for example, of different sorts, in which the red bars here correspond to some fraudulent. It has to do with somewhere in New York State, in which they just don't follow this logarithmic law. If you work out what you are paying to your employees and yourself, and then you fix the figures, then it doesn't sit up here. Anyway, what I'm going to be telling you, it's just following up work by already some years ago by Pietro Nero, the two Tossi, I think this is a couple, and Alessandro Vespignani, and going to tell you about an analogy again with this tangent bifurcation, and that it points out a possible statistical mechanical structure for these two laws. So these first two lines are taken from their work, basically. The law of Benford corresponds to uniform distribution on logarithmic scale. So this would be the probability of observing the data capital N. And if it's uniform, you have this immediately. And therefore, this probability should be like 1 over n. And you can use it to calculate the probability of observing the first digit n of the number capital N, and it will be just a simple integration, and the result is this, which is the law of Benford. But you can go now a little bit further and say, let's also rank the total number of data numbers. I use this calligraphic N. And this rank would be defined in this particular way. I use the same probability here, and will give me this expression immediately. It's very simple. And but I would like to solve for the frequency of which numbers n appear in a hierarchical way, give them a rank, and this will give me this exponential form. So certainly this is not the law of Zipf. Associated to the law of Benford, or associated to this basic distribution for probability distribution for extracting the number n, just to be simply 1 over n, will give me to a rank function which is exponential, which is obviously not the law of Zipf. And let's make a statistical mechanical interpretation of the past view graph. And that's that this basic probability can be seen to be a microcanonical distribution for n configurations, meaning you have n configurations, then each one of them appears with probability 1 over n. It's a view of that distribution. If it's seen that way, then these two logarithms can be seen as entropies or Massier potentials, and these quantities, n of k and the maximum number function of the total number of data, could be seen as partition functions. I'm just threading through these possible interpretations. So microcanonical, this would lead me to these two quantities that would play then the role of partition functions or configuration of numbers, and then the logarithms would be just entropies. And then what was found in the previous slide, which I think was written here, this expression, would be seen as a familiar form, a Legendre transformation between two conjugate variables, the rank k and the inverse of the total number of data. Of course, this is only part of the scheme. You would not take this as being a Legendre transformation. It would be incomplete. This is a familiar expression, then you will have to eliminate one of the conjugate variables in favor of the other. You have to use, for example, a saddle point approximation, you will complete the process that it's traditional or expected to be. But let me say from the start here that an incomplete Legendre transform has an important use in the statistical mechanics. For example, the Landau free energy, or the Landau-Ginsburg-Wilson free energy is in the category of an incomplete Legendre transform, or is a partial summation of partition function. But that's what we are just laying on the table, one after the other. So the first one was to interpret these as thermodynamic potentials, then have these as an incomplete Legendre transform, and of course, given further information, for example, the form of this function, if it's specified somehow, you can arrive at other expressions such as the equation of state and so on. Now let's see what happens when the exponent in the power law is not 1, but it's different from 1. Say, larger than 1. This is, was considered actually the core of the paper by Pietronello et al. And they used it to generalize the law of Benford just by replacing alpha equal to 1 by a different value of alpha, and then you would have a variant of the law of Benford, and they actually, put it forward and looked briefly at some data. For example, I think there were data about earthquakes, and more or less put forward an example that was not the simple logarithmic example, that was different with a different value of alpha. But they also looked at the rank K of the total calligraphic n of data numbers, and they will give you this expression. And they they solve it actually for the case, the special case in which that one that has appears as the most frequent goes to infinity, and they, by doing that, obtain the law of Sif, and that's the content of that article, to show that there is a link between the law of Benford, provided it's generalized. First, not to the first digit, you can look at the second digit, the third digit, any number of digits. You just can generalize it first to the full number, and once you are there, you can do what is in the slide and obtain in a special limit power law for the distribution of the rank, and that's what's in there. And we took interest in the paper and did a very modest first step, which was just to consider this number finite. And in that case, we obtain this expression. We look here what happens in two particular cases. These are world population, and these other one are text, words in English. We were interested not so much in the regime in which you have a power law, but the behavior at small rank, and for that we use semi-log expressions, and we realized that we were fitting the data reasonably with the values of alpha that are shown here. But this expression has something slightly artificial. The rank K can run all the way to infinity in this scheme, this analytical treatment. So you're looking at the population of a city, and you arrive at 1 inhabitant, half inhabitant, and so on, or something like that. It's in a kind of thermodynamic limit. Now, here is just posing the question whether one would be entitled to call an analogy between the ranking of data and the tangent bifurcation that we've seen earlier on. And you would say, well, this is a long shot, why should we think of something like that? let's just see. We look at dynamics of tangency. This is just to remind you of removing the map from tangency via the addition of a constant term. And this thing here just tells you that it becomes complicated. Life simplifies a tangency, but there is nothing to follow here. If I have more time, I will go into some descriptions are really not necessary. So we have here the map of tangency. We have a trajectory, and I'm showing it in was it semi-log? No, this is just straightforward. So we have the iteration time, we have the value of the phase space variable x, and we just have here map, the fixed point map of tangency. And we have 3 examples I want to show you of so-called eigenfactors in physics journals. Not exactly the impact, but a slightly different measure. And what's interesting is that I'm showing you in semi-log scale not only the power law regime, but the small rank and large rank behavior and how it works numerically. Here we have pollution by country per capita, I think. And here we have industrial production rates and so on. But let me try to come down and conclude, since time is running. If we have learned anything about this. So I'm showing you, at least from representation of data, we are doing very well. But do we have any other thing to discuss? So we are going back to statistical mechanical interpretation. So we have this basic distribution, which basically is a scale invariant. It's a fractal-like space that is being sampled. So we have this basic distribution for the configurations or for the sampling of data. And we do, as before, look at now not at the logarithms of these quantities, but we look at the deformed logarithms according to the exponent alpha. We look at these numbers, n of k and n max, as partition functions or configuration numbers. We look these as generalized entropies. We have this expression that is obeyed by them. We again call the name of an incomplete Legendre transform and point out how the process of elimination of one variable in favor of the other would be completed. And let me just then say the following, that, okay, we're talking about, are we understanding in some way the possible omnipresence or universality of these collections of data? Are we learning why are they so common? Is it because, as in thermodynamics, there are very general laws that they obey, but what happens with particular cases? And if we follow this line of thought, what we are basically finding is that if we want to continue the description, the thermodynamic description of this problem, we need to know more about the data. Maybe how the data has been collected, or maybe how is the data available for certain type of problems. And here's just an illustration, one in which the recollection of data is a prerogative of the person who collects them. Whether the person decides to collect them uniformly in the variable n, or whether collects them, extracts them these are two examples, uniformly in n or exponentially in n, and so that we have these needed functions and we can complete the transformation. I'm just showing it to you to see what is in mind. To finish, I will just recall you that in the case of networks, scale-free networks, for example, the distribution, the degree distribution, the basic degree distribution it's a ranking function, and therefore whatever I have said about the ranking function of any data n of k applies to the degree, and so when I leave you this to ask something, to say it or believe it, or what is missing, or what is not convincing. I have another analogy, which I'm not going to show it to you, that was worked out before this other two, that has to do with critical phenomena, ordinary critical phenomena, just a fluid at a critical point, in which you have fluctuations at all the scales. You have clusters, say, of leasing model, spin up, spin down, and these clusters have a lifetime, and they can be described again analytically through the same type of free energy, a Landau input Wilson free energy, in which the clusters grow and collapse, and then in that region another cluster of spins majoritarily in one direction grows and collapses, and you have these intermittent behaviors, and you can model it the same way. So you can add yet another example of the manifestation of these particularly simple rooted chaos in different problems, and whether or not they are pointing out at some statistical mechanical structure that I tried to describe to you.
Thank you very much, Alberto. Is there any question or comment? Anyone might like to do? I have a question myself. I didn't understand very well in your double Cayley tree.
Mm-hmm.
I mean, in terms of real realization of that network, you mentioned some connection with the way that some disorder can be introduced, but I didn't get that.
Yes, I only mentioned it, so thank you. I can describe it a little bit more only. What is, in a sense, surprising is that you can define a regular network that will represent a crystal, even if it has this strange Bethe lattice expression, and find such transition and a mobility edge. That surprised us and also surprised our referees. That in fact there was a metal conductor transition associated to a regular network, and it was not supposed to be there. And that took us to the next step, which is to look at the mechanism of localization in this other system, in which you have a scattering of these quantum waves, and that the scatterers are embedded in the material, but random way, if you want, but doesn't matter how they are distributed. And that is a property that has been understood, I think, from the 70s, by Baer, people localization, but irrespective of the positions of the scatterers, you have that all paths that return to the original scatter have a reinforcement they are not destroyed by superposition, and that leads to an enhanced backward current or amplification that is the source of localization. That's basic. In our case, the double Cayley tree has a feature that, well, it's common to any metal lattice, that only two sides any two sides are connected by a single trajectory. So our model imposes this non-destructive superposition because of the simplest way that there is only one path returning back to it. So it captures that feature. That's it.
Any more questions?